Hello everyone, today I'd like to talk about fusion and NLP pipelines in general. It is based on our work at Saarland University in Germany, and there is an accompanying paper which was presented at AKBC. And I wanted to revisit this paper more in detail because it's conceptually important for another paper that I want to talk about later. If you've been following the research in NLP, you know that there are lots of tasks, lots of models, and lots of various architectures. Sometimes it's even hard to keep track of all of them. And specifically, I want to focus on knowledge-intensive NLP, such as question answering, fact-checking, language modeling, knowledgeable dialogue, and others. Very important are the sources of information and how they are utilized by the model. Some pipelines use explicit knowledge bases, while some retrieve over textual documents. Overall, they get confusing and it's hard to memorize all of the pipelines. That's why in our paper we propose a unified abstract model by which we can conceptualize pipelines for different NLP tasks. The goal is to make understanding models easier because it can be split up into several clear components, which are key extraction, retrieval aggregation, artifact, fusion, and actual model inference. That was a lot of information in one go, so let's go step by step. Traditionally, all models start with a query, then they do some computation and produce the output. Simple enough. They can, however, be improved with a knowledge-based access. Now there are two paths of computation, the original and one at the top. The new one starts with an encoder, which produces the key. This key is used by the retriever to access the knowledge base. What's commonly done nowadays is to use some dense representation of the query and perform a search with that. The next step is the aggregator, which compiles the results together into something called an artifact. This is any object that can be used to improve the model prediction. Finally, it is fused into the base model. Here I admit that I incorrectly used the term knowledge base as an umbrella term for any persistent storage or source of information. In fact, it can even be another model. Here you may example recall the 2019 paper by Fabio Petroni et al., Language Models as Knowledge Bases. Historically, there has been a large focus on non-parametric models. Those are not models which don't have any parameters, but models which don't have any fixed amount of parameters. Usually that means that the information they have is scalable. However, in the last 5 years, parametric models show to be immensely useful. Unfortunately, they suffer some issues, such as getting outdated after pre-training or lack of explainability. And this diagram is a generalization for knowledge-intensive semi-parametric models, which are gaining in popularity. There are more aspects to this diagram, and in our paper we talk about things like specificity, knowledge-based source, fusion, and types of keys and values. The most important generalized property that we identify is the fusion, especially the point at which it's fused, such as early or late, and the actual mechanisms such as addition, priming, or filtering. We can formally describe any model inference as a composition of functions, and the point of fusion is simply the place in which the artifact, lowercase c, becomes the argument to the fusion. No fusion doesn't use this variable at all, but early fusion takes it already at the beginning. In contrast, late fusion takes it just before the output is produced, and intermediate fusion is in the middle. The reason why we do all this is that when approaching model building from the perspective of the best practices for a given task, we may omit improvements that were made in the research of the other tasks. And we'll see later that, for example, enhanced language modeling prefers to use late fusion as opposed to question answering pipelines, which rely heavily on early fusion. The model dense passage retrieval from 2 years ago is a prototypical example of this abstract model. It's a model for extractive question answering, and I'll now explain how it maps to our paradigm. We start with a query queue, which is a text. We turn that into its vector representation by feeding it to a fine-tuned BERT model. On the other side, we have a knowledge base, which is simply a vector for every textual document, also computed using a BERT-like model. This is passed to a retriever, which simply retrieves the nearest neighbors of the query in the vector space. The reason this may work is that relevant documents to a query live in the area of the vector space. Apart from the vector similarity, however, the overall metric is also conjuncted with BN25, which is a more traditional approach to retrieval. At the end, this produces artifacts C', which are relevant documents to the query that possibly contain the answer, and the model computes the span based on them. That was just one example, but there are many others, and they are described in more detail in the paper. With each, we can see the clear separation to the aforementioned components, encoder, retriever, aggregator, model. One contribution of this conceptualization is that it helps us read and categorize new research, because we know what components to look for and that they have roughly predefined input and output. I skipped the other example models, but I'd like to comment on this one. This is the latest work by DeepMind, and it shows that this isn't just some niche subject. What they use is again a retrieval-enhanced language model, and they get comparable performance to GPT-3 with 25 times less parameters. We did a small survey last year and found that language models use very light fusion on artifacts from training time sources. Other models for question answering, fact verification, and knowledgeable dialogue use more early fusion with external sources. The natural question is, why is this the trend? Is it historical because of customs in a specific subfield, or is there some innate justification? One would think that the sooner the model has access to the artifact, the additional information, the sooner it can make use of it. If this is true, then early fusion should be universally better, but that's not what people use, and systematic comparisons are missing because of the low transfer of knowledge and concepts between subtasks. Finally, there is the more fundamental question, how does this fusion actually work? It's well documented that it works, so at some point it's going to predict results which are closer to the correct answer in the loss space. Each circle in the figure is a vector space, and the top row shows a model with late fusion and a model with no fusion. The bottom row shows a model with early fusion and a model with no fusion. In the late fusion case, it's pretty clear that addition of the artifact simply lands the computation vector closer to the called output. But in case of early fusion, it's not clear because regardless of whether you're going to utilize the artifact or not, you're going to apply the same function. One hypothesis, therefore, is that by using the artifact, the model computation goes to a better place in the intermediate space, from which it's easier to produce the better output. To wrap things up, we saw that many knowledge-intensive NLP models are actually very similar if you look at them from a perspective of an abstract model. There is also a strong empirical evidence that 7-parametric models with fusion simply work well and have some good properties such as scalability and explainability. However, there are underexplored fusion combinations for many NLP tasks, and it's not clear what does the fusion do theoretically. Finally, if one decides that they want to use fusion in their model and improve it, there's a big gap in literature with advice which mechanism to actually use. I hope you enjoyed this presentation, and if you have time, please read the paper. I'm very open to any feedback and happy to discuss future research directions.